Hello, Hardi. How are you?
Hello, good afternoon, sir.
Good afternoon. How are you?
I'm fine.
Have you attended NXP seminar yesterday?
Sorry, sir?
NXP seminar yesterday was there.
No, sir.
You got message or no?
No, sir. Message was not sent.
I said one of the student, Jamie, circulated. There is an NXP campus drive going on. Good afternoon. So let's begin with our session. Yes, anyone got the message to attend the NXP seminar? I asked Hardi, but she got the message. NXP seminar.
No, sir.
Anyone? Okay. So NXP, maybe you know the company name, NXP Bangalore. Every month, 2 times, the expert from the NXP deliver the seminar of 1 hour. And what companies doing, what are the requirements from the VLSI engineers, that discussion is going on. So up till now, 2 sessions are over, and that is up to December. So I will share the link with you. You just register and you attend the seminar from the NXP expert. Yesterday it was there. That is all about for the SOC design. What are the job opportunities, the automobiles for the VLSI engineers. So I will share the entire information. You just use the registration link. You will get the access of that seminar. My screen is visible.
Yes, sir.
Yes, sir.
Okay, so let's begin our task of VLSI physical design on virtual mode. So this is three major blocks we have discussed yesterday. Final requirement is the layout, that efficient layout that we have to give the foundry. So foundry people can design our circuits. Circuit is too complex. With pen and paper, we are not able to design the layout, so we have to take the help of the CAD tools, computer aided design tools. Inside these tools, so many steps we are going to follow to generate the complete and useful layout. Our input side, we have to apply some digital circuits. Why not analog circuit? Can anyone quickly give the answer?
Because sir, all the inputs are analog, like whatever sensor input parameters various that are all analog signal in our environment.
But why not we use this entire flow layout generation analog circuits?
Sorry, sir, you are not audible.
Why not this layout generation with CAD tools with analog circuits for analog circuits?
Because digital circuits are more immune to noise, and various signal processing is also very easy with digital circuits.
Okay, let me give the exact. You know this name SCL Semiconductor Laboratory. Semiconductor Laboratory, which is in Chandigarh. So once we are in campus, definitely maybe in the month of March, we are going to visit this STL visit at SCL Chandigarh. Full foundry that
Sir, you
design
are
the
not
chip.
audible. Sir, you are not audible.
Hello, now?
So your voice breaks in between.
Hello, now?
Yes, sir, now you are audible.
So the company that's Semiconductor Laboratories at Chandigarh. So probably in the month of March, once you are here, you are going to visit this industrial visit, SCL Chandigarh. So it is a foundry specifically for SAC ISRO. All the ICs is fabricated for the SAC ISRO applications. This foundry is 180 nm technology. So what is the channel length?
180 nanometer.
Of course, it is 180 nanometer. So all the machineries, all the processing, which is applicable only and only for 180 nanometer. Now, if we pick up any analog circuits, maybe PLL, maybe ADC, maybe amplifiers, like that, you will never and never come to too much complexity. Complexity always very less in this all PLL ADC amplifier circuit. The reason is that there are so many constraints need to be satisfied, so many specifications need to be satisfied to design this all analog circuit. Not only just few or 3 to 4 like in the case of digital, but in the case of analog, so many constraints you have to satisfy in such a way that the complexity of analog circuit is very less. So maybe 100 transistor, maybe 150 transistors, you can design complete your PLL amplifiers, EDC, like that. So for this complex, less complex circuits, we are not going for this complete physical design flow. Complexity involved only and only with digital circuits. Plus 80% part perform so many performance parameters. 80% part is for the digital circuits with less constraint. So whenever less constraint is there, more complexity and more hardware is utilized for that purpose. Complexity is less constraint. The analog design, there is no use of any typical physical design flow. So choice for physical design, okay, choice for physical design is our digital circuits. For that, we have to pass the digital circuits step-by-step process so we can generate efficient layout. So this is the main agenda of today. We are going to see the why digital circuits and what are the performance parameters we are going to see before actually designing the layout. So we are going to focus the performance parameter of digital circuits. Am I audible now clearly?
Yes, sir.
Okay, thank you. Okay, so digital circuit performance parameters we are going to check, and based on the performance parameter, once we know, yes, this is the requirement of digital circuits, that we call as a constraint also, sometimes we call as a specification also, and then we move this into the CAD tools or different steps. So first and foremost, performance parameter for digital circuits is the delay. We call as a propagation delay. So let's we pick up some digital gates. We apply some input and we'll see how the output is look like. These are also in your, these terms are well known to you in your BTech level undergraduate course. We apply some square wave input and we are expecting some output also. So propagation delay is a time required for signal to travel from input to output. Time required to travel the signal from input to output. So if it's ideal device, ideal NOT gate, in 0 time you can transfer the signal from input to output. But reality is not ideal. We have some practical situations, practical gates are available. So in that case, we cannot say there is a 0 delay provided by the particular gates. What is available inside this gate? Can anyone tell me? What is inside this gate?
Transistors.
Transistors, yeah.
Transistors.
So inside this gate, transistors are available, and whenever you find a transistor, always there is a PN junction, and whenever you find the PN junction, always and always there is a parasitic or stray or internal capacitor or junction capacitors. Capacitors are always there whenever you find the PN junction. So in the MOS device also, as well as in the BJT also, or in the diode also, always here some parasitic components. So let me sketch the two square wave. Which signal is high frequency signal? First one or second?
Second one.
So second one.
Second one is high frequency signal. First one is low frequency signal. And because of this is, let's say, my input, okay, low frequency as well as high frequency. Because of the parasitic involved, capacitance involved, charging and discharging of the capacitor involved inside the device, and our output responses look like this. Not exactly follow the input, but it is look like this. Second case, it is also there. You tell me in which case it is more noticeable. In which case it is more noticeable, low frequency or high frequency?
High frequency.
Yes, answer is correct. Why?
Because if device is working at very high frequency, then the delay constraints are very significant.
So you cannot ignore this change and this change. Almost you have to consider. While over here, in the large spectrum, if there's a change is there, you normally ignore that change. Okay? Almost your curve is flat, square wave, perfect square wave. But if the change is in the small time, if the change is in so small time, you cannot neglect that effect like this. You have to definitely worry about that change. So whenever we use any circuit for high frequency application, 3.6 gigahertz nowadays. So you cannot ignore the device delay or parasitic involves in the device. Definitely you have to consider that delay, otherwise delay violations are occur which degrade the performance of your circuits. So high frequency applications always will worry this change as compared to the low frequency applications. So propagation delay is a term which is used to define change in the input voltage as well as change in the output voltage. So let me sketch my input. This is my V of E. Typical definition is here to take the 50% of the input. This is again well known standard at the VTech level. And if there's a change in the output, for change in the output also you have to pick up the 50%. So 50% of input and 50% of output. This is defined as one of the relay which is called PPHL, high to low. So whenever we take 50% of input, these are the measurement criteria, and the 50% of output, what is the delay TPHL is defined for that purpose, and at the same time for TPLH also. If you take the average of these two, we call as a propagation delay of that particular gate. So this propagation delay normally deal with the speed of your gates, or once you combine so many gates, we are going to design the system that ultimately decide at which speed your system is going to be operate. So there are so many criteria we have to consider for avoiding this violation of the delay and everything. So gate delay is very important. You have to worry about the gate delay because of internal capacitance presence inside the delay. Can anyone tell me what is the advantages of this delay? Yes, I sketch one circuit, very popular circuit. Can anyone tell me the name of this circuit?
So astable
It is
vibrator.
ring oscillator.
Ring oscillator, exactly. So yeah, ring oscillator. Name is ring oscillator. So ultimately, for other side, some delay is available. You can use that circuit as also without any input to generate power. Because of the gate delay. Because of the gate delay. So for some applications, maybe RF and all that, you need some ring oscillator kind of mechanisms. You can use this mechanism. But at the digital side, we have to worry about the minimum delay. We have to always take care from minimum delay. So our speed of our system, entire system should be higher. Apart from this propagation delay, we have also associated with that two others timing, which is called rise time as well as fall time. So fall time is nothing but from 90% to the 10%. And 10% to the 90% is our rise time. So these are also the delay parameters that we have to worry, which is defined only from the output. Rise time and fall time, which is defined only for the output signal. How fast it is changed from 90 to 10 and how fast it rise from 10 to 90%. So propagation delay, ultimately we have to worry as a input to output transitions, rise time, fall time only for the output signal, how quickly it is changed from 10 to 90 as well as 90 to 10. Let's move for the typical digital circuits. Somewhere in the orientation, I told you that digital circuits has a major performance parameters. One is speed, okay, that what we have seen the propagation delay. Okay. Second performance parameter is come out to be power. Major and major nowadays is work is going on how we can handle this power budget. So let us try to understand this with some example also later on. Can you define this function of this circuit? What is the name of this circuit? Or let me ask, what is the power dissipation of this circuit? What is the power dissipation of this circuit? Yes, can anyone tell me what is PD, power dissipation? Hello? What is the power dissipation of this circuit? Can anyone reply?
DC into I.
Yes, supply is UCC. How much time you require to give the answer for this simple circuit? That is straightforward. Power is nothing but always voltage into current. DCC is my voltage and I is my current. I hope you all are writing also in your notebook because these fundamentals require for interview as well as upcoming examinations. These are not a very high-fi questions I am asking. Just basic question. So power supply is power dissipation is VCC into I. Now, can anyone tell me what is the current passing through the capacitor?
C dV by dt.
Yes, C into change in voltage. Okay. The change in voltage is normally in digital case we call as a logic swing. Call as a logic swing, which we define as a VL. So it is called maximum to minimum change in voltage. It is called the logic swing. Divided by delay we call as a current passing to the capacitor is C into change in voltage, here is by delay, or delay we can write CVL by I. So by looking these equations, always you can say that there is a trade-off between speed and power. Okay. If you require smaller delay, that means high speed, you have to pay for the large current, and vice versa. If you require low power, definitely you have to compromise for the speed. Delay is larger. Always there is a trade-off between speed and power. Both you cannot achieve at the same time. So can anyone define what is a figure of merit from these two equations? Very important FOM, which is called figure of merit. Can you multiply power into delay? Both equations. What you will get? Just quickly. Multiply
C
this.
square.
I is cancelled. So VCC, how much time you require? I don't know. Everything is available on the screen. Is it correct?
Yes, sir.
Do not take too much time because I hope you are watching all this on the live online. So what I'm asking, give the response at least. If you don't know, also give the response. So power into delay, which is called the power delay product. It's identified as a figure of merit, one more figure of merit, apart from individual power dissipation or individual delay. It's called power delay product. So is there any current term in this formula?
No, sir.
No. So power delay product is always constant. That you have to worry for not independent current or independent delay. If you worry for independent current and delay, always there is a trade-off. Current is high because of change in this R or something like that. To worry about speed. But most of the design companies of ICs, they are specifying the power delay product. Power delay product is a constant term, independent of current variations. Or can say that maybe you heard about the different type of logic family like ETL, CL. For that, manufacturer provide this kind of graph, which is called power delay graph. So the log scale, if I sketch the graph, this look like this. Somewhere TTL is available somewhere over here. TTL is transistor logic. Maybe somewhere over here, emitter couple logic is available. And somewhere over here, I square L logic is available. These are all the logic families. For that, power delay product is defined. So on this graph, ECL, the power delay product is available. Here, this power delay product is available. And somewhere over here, for I square logic, power delay product is available. So it's instead of defining individual power and delay, now there is a trend of power delay product. PDP. So ECL, emitter couple logic, transistor logic, I square L logic. For all this purpose, this power delay product is defined. Now it's identified as a figure of merit. Figure of merit. If you understand, then we can move next.
Yes, sir.
So let us take one example. So all of you write down C equal to 50 femtofarad. We take some number. C is my capacitor, which is 50 femtofarad.
Sound is breaking.
So your voice is breaking.
Capacitor is 50 femtofarad. So okay, now VCC is given to you 3 volt and logic swing is given to you 0.5 volt. Am I audible clearly now?
Yes, sir.
So these are the numbers we are going to take. Capacitance is 50 femtofarad, VCC is 3 volt, which is my power supply value. Logic swing is 0.5 volt. Now, very important criteria that is called the packaging. So packaging is defined based on the cost. Price is decided by the what package is available for particular IC. So let's say I say that there is a 1 watt package. 1 watt package is available. If package is 10 watt, that cost is larger. At present, I have 1 watt package in that I have to accommodate the required number of transistors. So let's say I take two cases. Case number 1. First case, let's say I take the define the delay. Okay, which is 100 picosecond. I'm designing very high speed circuit whose delay is 100 picosecond. Can you calculate power dissipation per gate? Use your calci. Now onwards you have to keep calci also with you apart from pen and book. What is the power dissipation? Use that formula. PD into TD.
Sir, one question is from my side. What do you mean by
Yes.
1 watt package? What is the meaning of 1 watt package?
So 1 watt package is given, and by using this speed to achieve this speed 100 picosecond, we are going to calculate how many number of transistor or how many number of gates we are going to accommodate only in this small package, which has a 1 watt.
So is it the limit of that? Suppose we are manufacturing IC, right? So
Yes,
is it the limit of power dissipation of that particular IC?
yes.
Okay, fine.
So give me the answer of PD, which is my C, VCC, VL by TT. All of you calculate. Do not just wait for other to give the answer. If you are getting the answer, write down in chat box. Point 0.75 millivolt. Correct.
0.75 milliwatts.
Per gate. So can you calculate number of gates now? How many gates you can accommodate? Yes, someone quickly calculate Pujan.
So 1300 into so 1333.
Yeah. 1 watt divided by 0.75 milliwatt. This number of gates you can accommodate in 1 watt package if you want to achieve 100 picosecond high speed. This is case number 1. Can you turn off your mic? So I hope this case number 1 is clear to you. Speed is given 100 picosecond. Package is fixed 1 watt package. So we calculate power for each gate and then we calculate number of gates, 1300 almost. 1300 number of gates. Is it okay for you? This case number 1.
Yes, sir.
Let's go for
Yes,
case
sir.
number 2.
Yes, sir.
Second case. Now I have a very complex circuits whose packing density is very high. I require 10 raised to 5 number of gates per package. It's a very complex circuit where number of gates are larger. Now can you calculate what is power?
Ten microwatt.
Yes, 1 watt divided by 10 raised to 5. So 0.01 milliwatt. Okay. Now can you calculate what is delay? VDD VL by PD. If you are getting the answer, write down in chat box. What is the delay now in this case? Someone got the answer. Pujan is very quick. I like it. Pujan, nanosecond में बताओगे? Yeah,
75.
7.5 nanosecond per gate. So by looking these two cases, what is your comment? What is your conclusion?
So by increasing the gates, delay is more.
By increasing the gate 10 raised to 5 gates, 7.5 nanoseconds is ideal as compared to 100 picoseconds. But at that time, we accommodate only 1300 gates. Yes, any other observation?
Sir,
Power dissipation is, yes.
low power required per gate.
That is also trade-off. Okay. So by looking this case 1 and case 2, you can say always there is a trade-off between speed and power. Both you cannot achieve at the highest at the same time. So if you want to accommodate 1300 gates, definitely the speed is not high speed 100 picoseconds, but little bit power 0.75 milliwatt per gate. At the same time, large number of gates are there.
Sir,
Definitely
you are
the
not
gate
audible. Sir, you are not audible.
now. Now
Sir,
am I audible?
Sir,
I have a
sir,
question.
your voice is cracking.
Voice
Indeed.
is cracking.
Yes.
Let me disconnect. Just a second. Now, hello.
Yes, sir. Yes, sir. It's fine now.
So the conclusion is that if we are
Sir,
going to, yes,
sir, due to breaking of voice, I can't understand what is VL. That
yeah.
is,
VL is a logic swing. Suppose my output maximum is this one 5 volt and minimum output is, let's say, 4.3 volt. So this difference is called the logic swing. You get it? VCC is my supply voltage 3 volt. Capacitance is 50 femtofarad. I have a fixed package of 1 watt. in that I have to do everything because cost is also the constraint. If I go for 10 watt, 100 watt, cost is increased, packaging cost is increased. So case number one, where I pick up the high speed circuit 100 picosecond, for that I calculate power, and then only I accommodate this number of gates 1300. Then I increase number of gates, but at that I have to compromise for the speed 7.5 nanosecond, which is large as compared to the 100 picosecond. So trade-offs is available between speed and power. Okay. So this is my second performance parameters after the speed. If you recall the any digital circuit, we have so many other constraints are there in the case of power. Why we always follow the enhancement type MOSFET in digital circuit? Any answer? Why we go always for enhancement type MOSFET?
So there is a no channel available.
So, yes,
Yeah,
sir.
it's normally off. So if you are using depression type or GFET, if you not apply any gate voltage, still it is on state that consume the power. So we have to use normally off, which is enhancement. So for switching application, this is a good choice, enhancement type MOSFET. So if you not apply gate voltage, no current, no power dissipations. But if you apply the gate voltage, current starts to flow, power dissipation is occur. So in the design, in the digital designs, we have two major power. One is called dynamic power and second is called static power. So dynamic is when circuit is in operation. If you apply some input and circuit start working at that time, whatever power is there, we call as a dynamic power. And whenever circuit is in op state, if you not apply any input, but still there is some power is some current is flow, that is called the static power. So can anyone tell me something about gray code? How it is different from our 8421 binary code?
Sir, only one bit changes at a time.
So it is a good or not good condition for digital?
That's
Good, sir. It's
Yeah,
very good.
number of transitions are here less as compared to this binary. So if you are using the gray code, if you apply that gray code, your system instead of binary, the dynamic power dissipation is going to be reduced. Dynamic, it means whenever circuit receive inputs and it gives the output at that time, what is the power dissipation? So gray core is preferable. So when you study the digital circuit, different types of cores, access 3 core, ASCII core, something like that. But actually in the application point of view, we can use here in our digital design to reduce the power dissipations. So gray code is a good choice as compared to 8421 or binary code. Apart from the dynamic power, we have also the static power. So as I said, that if you are not apply any input, still power is or current is there, which is called the leakage power dissipations or leakage current. You have one full course in the next semester, low power design methods. At each and every stage, you have to use some techniques in such a way that your power budget is reduced. The reason is that nowadays source and drain are very nearer to each other. 3 nanometer, let's say 5 nanometer. So if you not apply any gate voltage, still maybe chance of carriers to be flow, which is a leakage current. So nowadays the trend is for each and every design steps, you have to worry about the power, how you can handle this leakage power. That's why if you keep your cell phone nearer to your ear, your screen is not display. Am I correct?
Yes, sir.
So only also within that talking time, you can save your power to screen to keep the supply to the screen. Also, if we are not using our desktop, after some interval of time, it enters into the sleep mode to save this all unnecessary power dissipation. So power is a major issue nowadays because size of the transistor is too much small and it's a big issue as compared to the speed. In the early day, 90s and 80s, people are worried about the high frequency or high speed. But nowadays, because of small size of the device, people are also worried about the power. Speed almost we achieve at some saturation value. Speed is not a big issue, but power is a major problem. Okay. So let us, is it clear up to this what we discuss?
Yes, sir.
Yes, sir.
So we have started with the performance parameter, which is first the delay. Then we found out the power and then power delay trade-off. Now we are going for the very important performance parameter, which is called the noise. As I said something about noise for digital circuit yesterday. Can anyone recall me?
नॉइज इज अनवांटेड सिग्नल सर जो भी मतलब सिग्नल काम करना हो वो नॉइज है
Um, let's say you are working at 22 nanometer. One student is working at 22 nanometer and one student is working at 180 nanometer. Can you say if VDD or VCC is same in both case? Supply voltage. No, supply voltage is not same. 1.8 volt here and maybe 0.6, maybe 0.5. Okay, to save the power, you have to reduce the VDD scaling also, supply voltage scaling also. So if you go for lower and lower technology, definitely this number is very nearer to your noise components. So if you go for 3 nanometer, definitely effect is more. If you go for 7 nanometer, effect is definitely there. Yes, you can compare your supply voltage, almost it is equal to your noise signal. So for digital circuit nowadays, noise is also very important. If you are working in 180 nanometer, no need to worry too much because 1.8 is our VDD. If you are working in 250 nanometer, still no need to worry about noise because it is 2.5 volt VDD. Noise is very far away from this. But for lower and lower technology, this noise performance also you have to worry for the digital circuits because your signal is almost equal to the noise. So you don't know because of noise, maybe your logic function instead of logic 0, you will get logic 1. So noise is also very important for the digital circuits. So let me give you the example. Time is very quickly passed. 53. I cannot able to finish this noise, but still I give some idea. We continue tomorrow also, no problem with this noise performance. Can you tell me what is the function of this graph? X-axis is input, Y-axis is output. ये ग्राफ का फंक्शन क्या है, कौन सा गेट है डिजिटल?
Is it a load line?
No, I am
It's
speaking
inverter.
Inverter, sir, not yet.
It is inverter.
yeah, absolutely
Not
correct.
yet, sir.
Yes.
For 0 it is 3.3 and for 3.3 it is 0. And now I am totally discussing the digital circuit because 80% part I have to utilize in my IC. So this is pure our NOT gate. If we apply 0, output is 3.3. If I take 3.3, let me put few more numbers. Let's say it is 0.2, 3.1, 3.1, then it is 0.2. And what is the gain of this line? जो line है इसका gain क्या है? Slope.
-1.
-1.
So absolute value, we can say gain is 1.
Hmm.
Absolute value, if I say the gain is 1. So let's say I use this gate for my application. As you said correctly that it is a NOT gate. Okay, like this. There are a chain of NOT gate available. If you understand with the numbers and everything, so no need to mug up the everything. And whenever you face technical interview and if you explain with some number, your impression is good or as your understanding, fundamental understanding. So always try to explain with some numbers, with some examples like that. Okay, do not just say the definition noise margin is like this, noise is like this, speed is like this, power is like this. No, give some examples so it's better to understand and better to explain also in your interview. So these are the inverter chain. I expect that if my input is 0, output is 3.3, 3.30 like that. Okay, but if I'm taking the same chain of inverter, somewhere I am adding the noise, which is unnecessary part. Let's say that noise amount is 0.2, 0 is my here, 3.3 is here, 0 is here. What is the value here? 0.2. Okay, because 0 plus 0.2 is 0.2. Now if you see for 0.2 my output is 3.1. For 3.1 my output is 0.2. And if you sketch again multiple inverters, let me put here. This is without noise. Okay, and this is with noise. So if I put more inverters like this, for 0.2 it is 3.1, for 3.1 it is 0.2. What do you observe in this line? Maybe probably last question of today. What you see here?
When noise increase, the output ultimately
It is still 3.1, 0.2, 3.1, 0.2.
yes, as here
If you
from 0 to 0.2 increase, so the
if
output
you, if you
from 3.3
see
to 3.1.
if you see here in the first case, without noise, fully or pure 0, 3.3, 0, 3.3. But if noise is added, your observation, if you see, can any other answer? Noise is also propagate. See, very important sentence. If you have inverter graph like this, as you rightly said, this is inverter. If inverter graph is like this, okay, noise is also propagate. Are you getting this sentence? My
Yes, sir.
Yes, sir.
inverter characteristic is like this, which is straight line, slope is 1. And if I add the noise, without noise there is no problem. Perfectly it is inverter. But once I adding the noise, it is also propagate. That I don't want. Noise should not be propagate. Noise should be completely 0 or it should be attenuated. That is my requirement. So we'll do something modification in this graph and then we'll see how we can do that. And we achieve the output 0, 3.3 without any noise. So almost two parameters we discussed completely today. One is the speed and second is power, speed power trade-off. Third is very important, noise we are going to discuss. Till just we define the noise, how it is look like with this graph, this characteristics, input versus output. So 2 minutes, can you, if you have any doubt, you can ask. So discussion require full complete days, it's not ending, but we have some time constraint. We have to follow the time.
So for this fundamentals, if you have to clear fundamentals, so which will
Your voice is breaking. Can you repeat again?
sir, whatever you are talking to, suppose you have to clear this type of fundamentals, so which book you should
So
prefer?
there no any specific book, only I am saying that you have to follow. There are n number of books are there, as well as some online resources also there. So by the time I will also tell you that I will tell you there's a fundamental you can learn read this book. Maybe at your BTech level you have this title, as I also mentioned during the orientation. Sanmo Kang. It's a very
Sir,
good book for
if the noise is more than 3.3, then what will happen?
noise is more than noise is not very large as compared to signal. Up to 3.3 you can add. It's never larger than that. And if it is one more point I am telling you, let's say at present I added the noise with logic 0. But same time if I am start with 3.3, this is 0, then 3.3, and now I am adding the noise. So at that time my noise contribution is not plus, it is minus 0.2. I have to subtract, because noise lower is always significant as compared to larger. So minus 0.2 and 3.3, that is for logic 1.
सर
Hmm.
सर आप वो दोबारा बोल सकते हो हाई फ्रीक्वेंसी में व्हाई हाई इन हाई फ्रीक्वेंसी टाइम डिले इज मोर प्रोमिनेंट?
मैं थोड़ा बड़ा स्केच करता हूँ तो इट्स क्लियर.
हाँ 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 ओके.
करेक्ट. लेट मी टेक द न्यू वन. एक बड़ी साइकिल है ऐसी. You said as a low frequency, and this is a high frequency. This is not my actual handwriting, so sorry for that. I am gauge the signal which is affected because of the capacitor. तो यहाँ पे ये छोटा change होगा, then it follow the input. Same way it follow the input, and यहाँ पे थोड़ा छोटा change होगा because of parasitic. Now same if I sketch for this high frequency. In less time change you cannot ignore. In large time change you can ignore. That is the concept. यहाँ छोटा change भी होगा वो that can be noticeable like this. So high frequency you cannot tolerate this change, while in the low frequency you can almost ignore. The 10 hertz frequency you cannot worry about this change, but it is a 10 megahertz. In very less time the change you cannot neglect. I hope it's clear to you now.
How much is noticeable in high frequency like this change?
So if there is a actual signal is like this, but instead of that if you are getting like this, so this change is not allowed.
Okay.
It is noticeable. But if you have signal like this and somewhere your output is look like this change and this change you can almost negligible. You cannot worry about in less time change. You can always worry about you cannot worry about large time change. You can worry about less change in the less time.
Okay sir. Okay, got it sir.
Okay, so thank you for joining. Because of time constraint we are not able to finish that noise part. Definitely we'll discuss on Friday. So on Friday you have to keep the laptop with you because we are going to do some stuff on the software. Okay.
Yeah, thank you, sir.
Okay, thank you, sir.
Thank you for joining.
Thank you, sir.
Thank you, sir. Thank you, sir.